Hello everyone, my name is Angie Poggi, and in this video I am going to discuss the one-way analysis of variance, also known as Anova. In my previous video, t-test for two independent samples, I discussed how we can determine differences between the mean of two groups. In this video, we're going to discuss how we can determine whether there are any statistically significant differences between the mean of more than two groups. Anova is known as one-way analysis of variance because there's only one grouping dimension or variable. The variance due to differences in the quantitative variable of interest is separated into A, variance that's due to differences between individuals, between groups, and B, variance due to differences within groups. Then the two types of variance are compared with one another. The between groups variance is due to the treatment differences, while the within group variance is due to differences between individuals within each group. The null hypothesis of an Anova test is that all means of the variables of interest are equal between the groups, while the alternative hypothesis is that at least two of the means are different. The test statistics for Anova is the F value, which is given by the variance between groups divided by the variance within groups. This formula compares the amount of variability between groups, which is due to the grouping factor, with the amount of variability within groups, which is due to chance. Evidence of non-random differences between group means occurs when the variance between groups is much greater than the variance within groups. To manually compute the F value, we must compute the sum of squares for between and within variability and the total. These steps can be tedious, but basically, the between groups sum of squares is equal to the sum of the differences between the mean of all scores and the mean of each group score, which is then square. The within group sum of squares is equal to the sum of the differences between each individual score in a group and the mean of each group, which is then square. The total sum of squares is equal to the sum of the between groups and within groups sum of squares. Once we have our test statistic, we will compare it with the critical value of F associated to the degrees of freedom for the numerator, which are given by k minus 1, and the degrees of freedom for the denominator, n minus k. Finally, we will decide whether or not to reject the null hypothesis and draw conclusions based on the research question. Let's do an exercise. The exercise reads as follows. Data were collected to determine whether the amount of stress is different among three groups of employees. Group A consists of employees who work the 7 a.m. to 3 p.m. shift. Group B employees work the 3 p.m. to 11 p.m. shift. And Group C consists of employees who work the 11 p.m. to 7 a.m. shift. We will complete this exercise using Statcrunch. To do so, first organize the data where each column is a different group. You will click on Stat, Anova, One Way. On the One Way Anova window, you will select all groups you wish to compare. In this case, we select all three groups. Statcrunch offers some options related to Anova to be used based on our interest. Once you're done selecting the corresponding variables and options, click on Compute. The output will show the summary statistics for each group and the Anova table with the degrees of freedom, sum of squares, mean square, and the F-stat value, along with the p-value. In this exercise, the p-value is less than our default 0.05. Therefore, we can reject the null hypothesis and conclude that we're 95% confident that the mean stress score of employees between the three shifts is different. From the column statistics, we learned that the 7 a.m. to 3 p.m. shift has the lowest stress score, while the evening group has the highest stress score.